As a reminder, Earth's eccentricity is 0.016, so that's that vertical line right there. And the planets of interest for us in terms of this talk are E, F, and G primarily. Those are the ones that are squarely in the habitable zone today. And the observations constrain the eccentricities to be less than about 0.1, excuse me. So this is sort of the range in which the planets might exist today. So there's a real chance that some of these planets are much more like Io than like our own planet. Now that doesn't mean they can't have life. You know, it just has to be fast life that outruns those volcanoes. But nonetheless, a very different kind of world than what we're thinking about in terms of Earth-like, right? These are not necessarily Earth-like worlds. And even if they don't have supervolcanoes every week, they still are different. They behave differently from our own planet because they probably do have significant tidal heating. All right, so moving on. Another interesting possibility that I mentioned is that the gravitational interactions between planets can do terrible things to planets. And you know, in our solar system, the planets are nicely coplanar. They all orbit in the same plane. That's not necessarily the case for exoplanets, and indeed, some systems have been observed to have relative inclinations of the orbital planes of 30 degrees or more. And so you can imagine that these planetary systems evolve very differently than our own. They're not going to behave like our solar system does with nice regular motion. And I'm going to show you here a movie of a system that's hypothetical. This is not TRAPPIST-1 anymore. Now I'm just going to thinking to the future, where we're going to think about a solar-type star. So we're going to get away from some of those issues like tidal heating and the early brightness of the star and think about, okay, maybe those planets aren't ideal choices for us to spend our telescope time on. Let's get back to thinking about something that's more like the sun and the Earth. You don't have tidal heating or a long pre-main sequence phase there. So in this case, I've set up a system with my computer that has an Earth-like planet at 1 astronomical unit orbiting a 1 solar mass star. But what I did is I kicked up the eccentricity and the inclination of the Earth-like planet, as well as a Neptune-mass planet that I put in a 3-to-1 resonance. And what I mean by that is that for every one time that green planet goes around the star, the Earth-like planet goes around 3 times. Right? So sort of like the Galilean moons, but a slightly different ratio of periods there. On the left is a top-down view of the system. Right, so kind of how we normally see our solar system when we look at it. And then from the right is sort of an edge-on view. But edge-on is a bit of a loose term here, right? Because you can see that that Earth-like planet is significantly inclined, something like 45 degrees. At the bottom are some bars that are going to show you how the eccentricity and inclination behave. And then when I'm going to play this movie for you, and basically this is an n-body simulation, meaning what I'm doing is just calculating the force of gravity between these 3 worlds, meaning about 3 planets and 2 planets in the star, and I'm just going to follow the gravity as it moves around. And on the left, I'll just point out that the little tick marks are where the planets are closest to their star. All right, so I'm going to go ahead and turn this movie loose, and you'll see how you'll see planets behaving badly. So here we go. Things are cooking along here, and you can see that the orbits start to do crazy things. It turns out that this is chaotic motion, but what I was found most fascinating about this is that this motion, although it doesn't repeat, it does sort of continue on in a quasi-regular fashion for 10 billion years. I couldn't break this system. I couldn't make the planets collide. I couldn't make one of the planets be ejected from the system. Instead, the orbits just evolved like this in a chaotic way for 10 billion years. So let me go ahead and play that for you again now that you know what to expect. So you can see, especially, so pay most attention to that orange planet, right? That's the Earth-like planet. 1 Earth mass, 1 astronomical unit. And you can see, especially, look at that eccentricity down there, right? It's that shape of that orbit. At about 912,000 years, the eccentricity reached a value of 0.99997. So that's basically as eccentric as a planet could possibly be. And it turns out that in that situation, the planet would actually collide with the star, which I treated as a point mass here. So not exactly what we would call a self-consistent simulation, but nonetheless, the point was just to sort of show that there's really almost no limit to how chaotic this motion can be if a planet is in a resonance. And so looking forward to maybe not this decade, but decades from now, when we can start to find these planets, we want to pay attention to what that planetary system is doing, because that can really impact the habitability of a planet. So, taking a little journey here from the habitable zone, thought about how we can push and prod it, and I think what I've concluded, and I hope I've convinced you of, is that this picture is insufficient. This is not enough to understand if a planet is habitable or not. And indeed, what I've shown you here is not an exhaustive list of issues that a planet may face. We haven't talked about formation, we haven't talked about those other bioessential elements. We've talked a lot about things like, is it orbiting the habitable zone? What's the tidal heating? Some of these small effects, but these are just processes that I've really focused on in the last 5 or so years. And I'm sure you all have, or many of you have, some ideas as to what your favorite issue with a habitable planet is. And these are just a laundry list of possibilities that you have to worry about, ranging from not just the character of the star in the orbit, but just how fast is an atmosphere lost? Do you need a magnetic field? Impact rates. And then you also can wonder about planets in exotic systems, things like planets orbiting brown dwarfs or exomoons, planets orbiting binary star systems. There's a whole host of possibilities out there. It's a great big universe, and we want to be ready for whatever kinds of planets we might discover that are in a position that's favorable for the observation of their atmospheres, and hopefully a diagnosis of whether they're infected with life or not. So really what we need to do is go not only just from beyond the habitable zone, and also beyond everything I've talked about already, and think about the real big picture. How do we connect everything to develop a comprehensive model for planetary evolution? So this is what we've been doing in my group for the last few years, is really trying to think about this problem. And I showed you that list of processes before, and I want to now show you a picture of my mental picture of how we do this. And I'm going to start with liquid water again. That's really still the bottleneck. But as you think about all these processes that matter, you get a picture that looks like this, where in the top left are what are processes we might generally call stellar effects. The top right corner is orbital effects. And then the bottom right is basically interior and surface effects. And the bottom left is atmospheric effects. And I don't have time to go through all of this, of course, but the point is that we've at least started to map out all of the different processes that really impact how a planet evolves and can be habitable. And when I first made this figure, it obviously wasn't quite so artistic, but it really, I recognized that not only was it daunting, I mean, we like to call it the planets are hard diagram. We also sometimes call it the habitability confusogram. It's obviously a daunting situation we're in, but I also saw it as a roadmap. That this was a path forward to understand how planets are habitable. And so over the last decade, I've embarked on this journey of trying to build a piece of software that could actually model all of this. It could simulate all of this together. And I call that software package vPlanet, the Virtual Planet Simulator. And what we do with vPlanet is we divide up all the physics that are relevant, and we create a modular software framework by which we can apply the different physics, whether it's the orbit, whether it's the atmosphere, the galaxy, whatever kinds of problems or phenomena we're interested in, you can plug and play those kinds of processes into this software framework and simulate any planetary system with any planet that might be habitable. You can, of course, simulate a lot of planets that aren't habitable as well. So it's sort of a platform for planetary science that will allow us to gain a lot of insights on exoplanets and hopefully even in our solar system as well. And so how do we do this? Right? So there's obviously some challenges here that I want to kind of meet head on and describe to you. So the first issue you might naturally ask yourself, is what I ask myself, is that there are so many phenomena we're talking about here. How can we actually do this? Well, how can we actually merge them all together into a framework that we can trust? Well, so vPlanet, we basically gathered together scientists from different disciplines, geophysicists, atmospheric scientists, stellar astrophysicists, and we brought in models that they had developed in their home disciplines, and we merged them together and validated all of their models against solar system objects and binary stars and the galaxy and things like that. So this code reproduces things like the magnetic field evolution of our planet, the obliquity evolution of Mars, the loss of water on Venus, tidal heat on Io, binary star systems. It does all of that in a single code, and then we can merge them at runtime. Which I guess is, I think, the next point I'm going to make. So, planets are in different environments. We need to have flexibility here. We need to be ready for whatever observers find for somebody like me to try and simulate. And so how do we do that? Well, like I said, vPlanet is modular. You decide at runtime what physics you want to apply. So you don't have to be limited in your scope. And I'll just say that the results that I showed you here were all developed with this code vPlanet. All the same executable, all the same piece of code. It did everything from the atmospheric mass loss to the crazy orbital evolution, and a lot of things I didn't show you. And so the other, but we still have to recognize this fact that there are literally hundreds, if not thousands, of parameters that we have to worry about in this situation. It is an absolutely daunting problem. It's mind-boggling to think about how we deal with this. So how do we do it? Well, as Mark mentioned early on, I'm a member of the data science program, and I've embraced this new field of data science that's also come around, and we're starting to use artificial intelligence, machine learning, to try and get at this problem and actually be able to turn it into something that's tractable. And so, in addition to vPlanet, we've recently developed this code that goes by this name of Prox Posterior. A graduate student has developed it, and it basically uses machine learning to decide how vPlanet should run through a parameter space to find those sorts of evolutionary histories that are consistent with observations. Right? So it's not about just blindly searching through this maze of 100 different parameters and dimensions. It's about doing it smartly now. And so that's what we've been working on here. I'm going to show you another technical plot just to show you sort of where we're going with this. Don't have to worry about the details too much here, but the point here is in the title of this slide, that this method that we've come up with is 700 times more efficient than what's been done before. Machine learning is amazing. And so this, on the left there is this panel that shows you a set of simulations that were done with sort of the way people have done it before, the sort of brute force calculation versus this artificial intelligence model. And you can see that the contour lines are almost the same. We basically nailed the problem. And so what I'm showing you here is that we modeled the star, TRAPPIST-1, and basically we wanted to try and understand 5 parameters based on 2 data points. So understanding the history of the high energy radiation of the star based on its currently observed luminosity, as well as in particular what's being emitted in the X-ray and the UV regimes of the spectrum. And what's critical here is that when we think about spending $100 million, we don't want just the best fit or best guess. We want to understand those uncertainties. We want to know, how likely is it that something has happened to this system before we invest all these resources that you've paid for. And just a technical point for those of you that care, this is all done through Bayesian statistics, which I think is the preferred way to do this. It allows us to understand how different parameters are related to each other and really start to tease out what observations might actually help us break some of the degeneracies that we see in these systems. How can we really make sense of them? And as I said, we want to understand the likelihood that a planet is habitable. Not just is it, but how likely is it, so that we can observe the best ones. And just to kind of show you what the point here is that you don't know what these parameters mean, and I'm not going to go through all these technical points here. What we concluded from this experiment is that for the star, TRAPPIST-1 is very likely to still be in this active phase. It's probably still a flare star that is emitting an enormous amount of UV and X-ray light, probably 1,000 times more high energy radiation than our sun is emitting. So these planets are being blasted by this high energy radiation that might be doing things like removing water, maybe even removing the atmosphere. All right, so that's great, that's really helpful, but there's still a problem here that there's a ton of variables, and now we're folding in this machine learning artificial intelligence business. And I think machine learning is powerful, but we need to remember that it's still just a tool, that real insight comes from the human brain. And so I didn't want to just trust what the machines tell me. I wanted to actually understand it for myself. But when you think about trying to look at plots of many parameters against each other, it takes forever to do this, and you're never sure if you're really looking at the right things. And that's where I got this. I got into this idea of visualizing the data through virtual reality. And so, as I was mentioned in the introduction, I founded a startup in Seattle we call VR Ulysses that is explicitly designed to help me solve this problem, so that when I look at hundreds of dimensions, I'm not trying to understand them on a screen like what's got in front of me, but actually using virtual reality. So I don't know how many of you have used this before, but virtual reality is pretty cool, and I recommend all of you give it a try. I got a little video here that shows you what this experience looks like. So basically, you materialize in what we lovingly call the bathysphere, and you have these data sets that you can pick up, and you do all of this with your hands, right? You don't type at a keyboard, right? Your hands didn't evolve to type on a keyboard, right? You want to grab things, and that's what you get to do in VR, is you grab things and you move them around. It's very intuitive. You pull handles and things like that. And you pick which data, what parameters you want to look at, and then they emerge in front of you, and you can fly through them. You can look at them from different perspectives. You get parallax because there are these two 1080p monitors that are 2 centimeters in front of your eyeballs. So you get parallax, you get that third dimension, and you can really see your data in a new way. And rather than having to sit and type out, all right, I want to plot stellar mass versus semi-major axis, instead it's you just swap them out. It takes 2 seconds, and you revisualize it, and you're able to scan through these complex high-dimensional data sets with relative ease and relative speed. So it's pretty exciting to see this capability starting to come to life, where we might be able to actually manage and understand these incredibly complicated data sets that aren't just unique to me, that they're pretty common throughout science now. And I want to thank Danny Tayar for this. She's a film studies student at Seattle University who's helping us understand VR. And I just wanted to point out a few interesting facts about VR that I think are pretty interesting. Our approach is to fully embrace virtual reality. We want it to be intuitive, like I said, no keyboards. We want it to be immersive. We don't want to do augmented reality where there are distractions. We wanted to completely embrace VR. And we wanted it to be interdisciplinary, which of course is my background as an astrobiologist. We didn't want this to be tailored to any one problem. We wanted it to be useful for everyone. And we wanted it to be quick, where you get that inspiration quickly. And there's some important advantages to VR in terms of science, which maybe you're not aware of. Of course, some of them are obvious, like this idea that there's a third spatial dimension you can look at. And in virtual reality, you're completely blocked out from the rest of the world, at least visually. And so you don't have any distractions. When I sit in my office, graduate students come by and talk to me or whatever, and it's great to talk to them, but at the same time I'm getting distracted. And in this way, I'm just completely engaged in my science problem. You also just have a lot more screen, for lack of a better word, or what I like to call the visualization canvas, to look at. You can look behind you. You can see so much more of your data. And like I said before, it's a natural process. It's not your keyboard. It's just much easier to use. And crucially, there are 2 physiological reasons why virtual reality is